Okay, so we are going to learn about Newton's three laws, and before we do that, we need to learn about something called uh, a free body diagram. Free body diagrams are a way for us to see what's going on and visualize the forces so that we don't have to keep it all in our head. You might see a free body diagram as a dot. I like to make free body diagrams as just a square, as if it's a mass. These represent the center of mass of the object, and when we draw free body diagrams and we draw forces, we're going to draw them from the center of mass. So imagine for a second a mass sitting on a desk. Or if you're sitting down and there's something in front of you, pick it up and hold it in your hand and just hold it perfectly flat. And I bet you can feel that thing on your hand and you know that you are holding it up. If you were to let go of it, it would fall. Why would it fall if you let go of it? And everyone's going to answer gravity. Okay, so there's this phenomenon known as gravity. It exists. On the Earth, we feel it. We feel the gravitational attraction between ourselves and the Earth. We know that there is this thing called gravity. And so if I am on the Earth or on any planet or anything, the first thing I'm probably going to do is draw the force due to gravity as my first force. So in a free body diagram, I simply, from the center of mass, draw an arrow in the direction that the force is acting, and then I label it. So if this is just a mass sitting on a desk, I know that I've got the force due to gravity down. I also know that the desk is there, and the desk is holding up the mass. That means there is another force up that we will call force desk. Are there any other forces on that mass? Not that we care about. The mass is at rest on the desk. Maybe it's your coffee mug just sitting there. There's nothing else to worry about. That's the whole thing. That's all we have to worry about. So very simple. What about if we have a ball on the desk? Does the picture change? No, of course it doesn't. If I wanted to draw a free body diagram directly on top of this ball, I would have the exact same picture. Now, these forces aren't going to be the same force. In other words, if this mass is a very, very large mass and this ball is a very, very small mass, they might have different forces due to gravity. Hey, by the way, when I say Fg, when I say force due to gravity, what am I really talking about? Weight. That's what we call weight. A 10-pound weight is 10 pounds because it weighs 10 pounds because the force due to gravity on it is 10 pounds. In this class, obviously, or in physics, in the science world, we tend to use newtons instead of pounds here. But it's really just a term that is interchangeable with weight. Okay, so no difference here. Now, let's say I take that ball and I roll it. I go into a hallway, I roll it down the hallway. Let's pretend we live in a world where there's no such thing as air resistance. There's no such thing as friction at all. I roll that mass and I just watch it. And at some point while it's rolling, I take a picture of it. And here it is. Look at that. There's my picture of it. Or I rolled it across the desk because I labeled this desk. How does this change the free body diagram? If we were in a class together and I asked you to draw what you think the free body diagram is, most of you will start the same way and you'll say, yeah, well, we're still on Earth. It's still a force of gravity. It's rolling across the desk. There's probably still the force of the desk up on it. And now there's the force of push. I hear that sometimes. I hear the force of motion sometimes. I hear a lot of things, but there isn't. The picture is exactly the same. Okay, let's stop and think about this for a second. Even though this ball is rolling forward right now, the free body diagram, all the forces on it are exactly the same as when that ball is just sitting there at rest. Yes, I said we're just ignoring friction. We're ignoring air resistance. Obviously, there is some friction, there is some air resistance, but we're going to just say they're not there for now. Maybe we're in a vacuum. However you want to think of this, we're going to pretend that neither of those things exist for the sake of argument right now. So these two things look exactly the same, but in one case the ball is in motion and in another case it's not in motion. How could that be possible? How? Well, what kind of forces do we have? We have two kinds of forces. We have what are called contact forces, and we have what are called field forces. What is a contact force? Literally, you have to be in contact with the object. You and I apply contact forces to stuff when we pick it up and move it and do whatever. That's what we do. We physically touch the object to apply our force. Then there's something called a field force. A field force does not require there to be contact with the object. The easiest example right now is the force due to gravity. Gravitational forces are field forces. When you take an object and you drop it and it starts accelerating towards the Earth, that is happening even though it is not touching the Earth. It's in the air, it's not touching the Earth, and yet the Earth is pulling down on it with a force. So when this ball is rolling across that desk or across the hall or whatever you want to envision when you close your eyes, or you just throw a bowling ball down a bowling alley, and halfway down that alley, nothing's touching it except for the floor, and it's still in motion even though there's nothing else pushing on it. There is no force of motion. That's not a thing. It's just going to keep going down the bowling alley, or down the lane, even though there's nothing continually pushing it. Okay, let's move on. Let's imagine we've got a rocket and it's just starting to take off. In this scenario, we've again got a force down. We still have gravity. And this time, we've got, I'm not going to call it, well, I will for now. We'll call it the force of the thrust for now. And then we'll talk about it later. We've got this thrust force upwards. Notice it's not the desk. There's no desk there. But there's something else making it go up. There's some force up. And now this rocket slowly begins to get faster and faster and faster and faster. I'm going to focus on this for a second because there's two important ways to potentially do this free body diagram. I wonder if this will be easier to see. When I draw free body diagrams, I have a tendency to ignore the size of these arrows. I don't know what the values are, and so I ignore the size of the arrows. However, if you are going to draw them to scale, or you're trying to use the arrows to help you visualize what's going on, this might be a scenario where you say, hey, wait a minute. I know there's some FG down, but I also know I'm overcoming that FG. So my thrust force, must be bigger than my force due to gravity down. And so this is another way that we can use this tool. We can make the arrow larger. I have a tendency not to do this. I have a tendency just to draw my arrows however long they are, and then I'll write numbers down if I know them, or I will just analyze in the situation which one must be larger. And finally, before we really get into Newton's laws, let's look at our last situation. Imagine, if you will, that this rocket has taken off from the Earth and it's on its way to the moon. And as far as we're concerned, it's far enough away from the Earth and far enough away from the moon that it's not feeling the forces from them. Those of you who are science buffs uh, have something to say about this, I'm sure, but we're just going to say, I'm so far from the Earth, I don't feel its force. I'm so far from the moon, I don't feel a force. And there's that rocket flying through space on its way to the moon, and it's all out of fuel. So it turns its boosters off. Or maybe it's low on fuel and it needs to preserve it for landing. So it turns its boosters off. When it turns its boosters off, does that rocket stop? Does it stop moving? Does stuff in space have rocket boosters constantly on in order to keep it moving? Of course not. So in this scenario where this is really far away from everything, it doesn't feel a force from the Earth, it doesn't feel a force from the moon. There's no up force on it, there's no down force on it, there's no forces at all. And yet, this rocket is continuing its velocity. It's continuing to move. So these are some things that we can very simply imagine and look at and okay, I've got a mass on a desk and it's at rest and these two forces are balancing and they're balancing. And this one, even though it's in motion, there's no forward force. That one might seem a little bit weird, but okay, I'm not pushing the ball forward while it's rolling. It's just out there on its own. And there's nothing pushing this rocket, and yet it's still just moving on its own. And so now that's going to bring us to what Newton's laws say. First of all, what have we determined from this? Here I have forces and there is no motion. So the first thing I know is that even if there are forces, it's possible there's no motion. So stuff can be at rest. And then I get to this scenario where there are no forces. And I have the opposite conclusion. Even with no forces, stuff can be moving. That's huge. These two ideas are huge. And these two ideas are often gotten wrong. Students assume if something is at rest, there are no forces on it. Or that if something is moving, there is a force providing that motion. But that is not the case. There's absolutely no force, and yet there is motion. So what are Newton's laws? Well, the first law we care about is that stuff does what it is already doing. That's the first law. Stuff does what it's already doing. I guess I should say, unless something else changes what it is doing. Or unless something else makes it stop. There we go. So stuff's going to do what it's already doing unless something else makes it stop. Unless something else comes in and says, hey, you have to stop doing what you're doing. And you have to do something else. That's Newton's first law. Whatever stuff is doing, it's going to keep doing. It wants to keep doing it. Okay, how is this really written out as a law? An object at rest remains at rest unless acted upon by a net external force. An object at rest remains at rest. Stuff does what it's already doing. So it's at rest, it's going to keep staying at rest. Unless something else makes it stop. And when I say the word stop, I mean change what you're already doing. So if you're at rest, stop being at rest. Now you're going to be in motion. If you're in motion, stop being in motion and change how you're moving. An object is at rest, remains at rest unless acted upon by a net external force. We're going to talk about this, don't worry. What else does it say? Well, it also says an object in motion remains in motion at a constant speed in a straight line unless acted upon by a net external force. There's some really important stuff here. Constant speed, straight line. So you're going to keep doing what you're already doing. I am moving forward at this speed. You want to change me moving forward at this speed? Put a force on me. Maybe you can make me move a different direction. Maybe you can make me speed up or slow down. It does not simply say an object in motion remains in motion. It's unbelievably important that that motion is a constant speed, and it's unbelievably important that we say that it's in a straight line, unless acted upon by a net external force. Net, meaning non-zero. External, meaning a different object has to provide the force. I can't provide the force to move myself. You think I'm wrong, but I'm not. Sit in a rolling chair. Take your arm and push on your chest. Are you going to go anywhere? No. You cannot apply a force to yourself and make yourself change your motion. Other stuff has to put a force on you to make you change your motion. I know you think I'm crazy, but we're going to go over this. So the Newton's first law is the law of laziness. And you're going to say to me, no, if stuff is already moving, that's not lazy. Disagree. How many of you have said to yourself, all right, I need to go out, and while I'm out, I'm going to run this errand. I've got to return this folder I bought. I don't know why you'd be returning a folder, but you get the idea. So you leave your house and you realize after you've gotten to your car, you left the object that you were going to return inside. And what do you say? You say, I'm not going back inside. I'll do it later. I've gone too far. I don't want to go back inside. So you're in motion. You're already in motion. And you can't get yourself to stop and go and turn around and get that thing. Even if you've only walked 10 feet out the door. I know that you all do it. You look inside, you look back towards the door, and you say, no, gone too far. Classic scene from Harold and Kumar Go to White Castle. Amazing movie about physics. And obviously on the flip side of the law of laziness, you want to stay in bed. You want to stay at rest. What's the only thing that's going to get you out of bed? The force of, well, you're going to be late. You're going to lose your job. You're going to be late. You're going to get in trouble at school. Your parents are going to yell at you. Whatever it is, you want to keep doing what you're doing. And it takes something else, some sort of external pressure to make you change what you're doing. Let's look at Newton's second law. Newton's second law simply says that there is a relationship between how much force is on something and how much that thing will accelerate. Okay, time out. Let's just look at this. It says there is an equivalency between the net force on something and the mass times the acceleration of the object. In other words, if the net force is 4 newtons, then the mass times the acceleration needs to come out to 4 kilogram meter per second squared, and that might have looked confusing. So for instance, it might look something like 2 kilograms times 2 meters per second squared, and so 4 and 4, there's an equivalency. They end up being the same. But what does it really say? What it really says is that a net force causes a mass to change its motion. aka accelerate. Acceleration is a change in motion. It's speeding up, it's slowing down, or it's changing direction. That is acceleration. So a net force causes a mass to accelerate. That is Newton's second law. That's it. It's basically just a mathematical equation. The more the net force, the more we expect the acceleration to go up. And obviously, the larger the mass, the smaller that acceleration. So let's just take a quick look. I'm going to not put units for a moment. Let's just say the left side again was 4. The right side has to come out to 4. How can I do that? Well, if the mass is 1, then the acceleration is 4. So that's a pretty large acceleration. But as my object gets larger, my acceleration gets smaller. So the larger my mass, the harder it is to accelerate it. The larger my mass, the harder it is to change its motion. Oh, let's go back to the first law. Because the first law is sometimes called, I already have it on, the law of inertia. And this confuses students. Students often get inertia and momentum mixed up. Oh, well, that's sad. Let's just undo this quickly. Students sometimes get inertia and momentum mixed up. Inertia, as far as you're concerned, is mass. Inertia is a measure of how difficult it is to change an object's motion. A measure of how difficult it is to accelerate an object. Inertia is mass. You haven't learned about momentum probably yet if you're watching this video. Momentum, you've heard of, oh, we're really building momentum. Momentum is a measure that has to do with motion. In order to have momentum, you must have motion. In order to have inertia, you can be at rest, you can be moving, it doesn't matter. All that matters is that you have mass. Changing your speed does not change your inertia. Inertia is mass. So the law of inertia, because you have inertia, you want to keep doing what you're doing. The more inertia you have, the harder it is to change what you're doing. A really, really big object is harder to change its motion than a really small object. So the more inertia, aka mass, you have, the harder it is to change your motion, aka your acceleration. Finally, Newton's third law, which you may have seen something like this. For every action, there is an equal and opposite reaction. So this is an oversimplification. Did I write a Q instead of an A? This is an oversimplification. I'm going to write it again, and I'm going to say for every force, there is another force that is equal in magnitude and opposite in direction. These two forces do not act on the same object. This is unbelievably important. Newton's third law tells us that if there is a force, there is another force. And that force is equal in magnitude and opposite in direction. But what people get wrong is they think that the forces act on the same object. They don't. This is called a force pair. Newton's third law is called a force pair. Here is the biggest mistake made about force pairs. Oh, Here's my mass sitting on my desk. I've got my force of gravity down. I've got my normal force up, and so the normal force and the force of gravity are force pairs. This thing is at rest. If the force of gravity is 10 newtons, Fn is 10 newtons. Look at that. Equal and opposite force pairs, done. Third law, expert. Wrong. Unbelievably wrong. If that were true, if this is how Newton's third law worked, objects could never accelerate. They could never accelerate. Because look, 10 up and 10 down is 0. They add up to 0. If I have 0 net force, I cannot accelerate because remember, if this side is 0, this side has to be 0. This is not Newton's third law. Force pairs have to come from different objects. So, what is the force pair of this force of gravity down? Well, I know that it has to be an up force. I know that it has to be 10 newtons, but I also know it has to act on the other object. And so now the question for a force pair has to be, what are the two objects putting forces on one another? And this is counterintuitive. You don't think of this. This is not what you are used to. But if that mass is on the Earth, and let's pretend the surface of the Earth is way down here. Here's the Earth. Maybe this thing was up on a desk. Well, then there is a force upward on the Earth of 10 newtons. What? That's crazy. Yeah. You're a 150-pound person because the Earth pulls down on you with 150 pounds. Well, guess what? You're also pulling back up on the Earth with 150 pounds. You have your own gravitational field. It's a very, very, very small gravitational field. Objects around you aren't really influenced by it because it's so small. And the Earth is so massive, it doesn't care. But that's the force pair. The force pair has to be on two different objects. And so the easiest way to think of a force pair is literally just to flip it around. The Earth is pulling down on me. That's force 1. Force 2, flip it around. I am pulling up on the Earth. So let's look at this 10 Newton force. This 10 Newton force up is being provided by this surface. Maybe this is a desk. Let's pretend it's a desk. Well, what's the force pair of the 10 newtons up? The desk pushes up on the mass with 10 newtons, so the mass is pushing down on the desk with 10 newtons. That's the force pair. Whenever you are given a question about a force pair, all you do is flip the objects around. A bat hits a ball, force pair, flip it around, a ball hits a bat. That's it. And the forces have to be equal. They have to be opposite in direction. They have to be the same size, guys. Must be. Force of gravity, 10 newtons down. Force of gravity, 10 newtons up. Desk pushes up on the mass with 10 newtons. Mass pushes down on the desk with 10 newtons.